Welcome to the debate. Today, we are diving deep into some pretty significant recent architectural innovations in large language models. Specifically, we're focusing on this new class of models called looped language models, or loop LLMs, and the prime example seems to be the Auro family.
Right, and the hour models have certainly stirred things up. They presented some really compelling, but I'd argue sometimes contradictory evidence about how model capability, how it truly scales.
Exactly. We're looking at models with, 1.4 billion and 2.6 billion parameters, and they're showing this remarkable 2 to 3 times parameter efficiency advantage, matching or even beating standard transformer models up to 8 billion parameters, especially, it seems, on tasks that need complex, sort of latent reasoning.
Which brings us squarely to the central question, doesn't it? Given these, unprecedented gains in efficiency, does the success of loop LM fundamentally establish loop depth, the iterative application of shared weights, as a genuinely viable independent third scaling axis for frontier models?
Or, the alternative view, are the observed gains just a highly optimized form of compute efficiency that, at the end of the day, remains constrained by the finite knowledge capacity? The capacity that seems irrevocably tied to parameter count?
That's the core tension.
And my argument today is that recurrence, as seen in loop LM, validates loop depth as a truly novel scaling axis. It's driven by these architectural improvements in, specifically, knowledge manipulation.
And I'll be taking a different perspective. While the empirical gains in efficiency are, frankly, quite significant, I'm just not convinced that looped depth functions as an independent scaling axis in the same fundamental way as, say, parameter count, n, or data size, d. My position is that these gains actually confirm that fundamental knowledge capacity is still parameter-bound. Loop LM's efficiency is a powerful, yes, but potentially fragile optimization designed to maximize the utility of that fixed capacity. We're making better use of the information we have, not fundamentally increasing the amount of information we possess.
Okay, let's start maybe with the mechanism itself. Knowledge manipulation versus capacity. For me, the core finding here, and it seems proven empirically across quite a few benchmarks, is that recurrence dramatically enhances the model's knowledge manipulation capabilities. And crucially, it does this without requiring any increase in raw knowledge storage. That's a critical distinction, I think, that establishes a new scaling principle. The empirical evidence really speaks volumes, especially when you look at tasks demanding compositional reasoning. On MMLU's elementary mathematics category, we saw the Oro models get a massive, 155.6% improvement just by increasing loop depth from 1 to 4. That's not just an incremental gain. That feels like a complete shift in capability for that kind of reasoning.
It's a striking number, definitely.
Right? And furthermore, Oro's 2.6b managed a score of 90.85 on the specialized Math 500 benchmark. It absolutely crushed the 8 billion parameter Qwen3 model, which scored only 62.30. These results strongly suggest that the iterative process provides a superior inductive bias for things like multi-hop reasoning and composing calculations.
Okay.
And beyond just the empirical benchmarks, the theoretical backing seems to support this claim of a new axis too. The architecture introduces a mathematically efficient form of latent reasoning. It's been proven theoretically to solve complex computational problems like graph reachability in highly parallel steps, specifically O of log d, where d is the graph depth. That suggests, exponential efficiency compared to standard sequential processing. This feels like a substantive scaling law derived from depth, not just size or data.
That's a compelling argument. I agree. The empirical numbers on those reasoning tasks are, they're shocking, no doubt. However, we have to respect the foundational data related to storage capacity. Controlled experiments, as reported, show pretty conclusively that looped models do not increase their raw knowledge capacity. They seem to maintain the same observed knowledge density, around 2 bits per parameter, as their non-looped baseline counterparts. So if the ultimate ceiling for general capability is fixed by how many facts and concepts the model can effectively store, and that storage is fundamentally parameter-bound, then Looping looks primarily like a highly effective method for maximizing the utility of that fixed data, not really bypassing the underlying constraint. And achieving this optimization, it also requires highly specialized engineering, which for me undercuts the claim of a universally robust scaling axis. The efficiency gains rely heavily on an incredibly complex training regimen. It involves two distinct stages, and critically, this entropy-regularized objective using a uniform prior. Now, to put that in more academic terms, the model, if left to its own devices, would naturally tend to exploit the loop architecture. It would just default to the maximum loop depth, Tmax, essentially wasting computation. They had to introduce this regularization term. It's a tricky mathematical penalty, really, to force the model to adaptively decide when to stop looping. This dependency on meticulous stability controls and a complex two-stage training process, it suggests the architecture might be inherently fragile, maybe prone to collapse without these rigorous, non-standard methods.
Okay, I see why you'd frame it that way, but let me offer a different perspective on that fixed capacity point. You emphasize the 2 bits per parameter limit, right? But the effectiveness of the looping architecture lies, I think, precisely in its improved inductive bias for using that stored knowledge. We're talking about an enhancement in algorithmic manipulation. The success of LoopLM on synthetic reasoning tasks, like the mono benchmark, which requires parsing complex arithmetic trees and composing calculations, it shows that given the same knowledge budget, the looped model possesses a better algorithm, if you will, for accessing and transforming that information. So it's not necessarily a storage problem. It feels more like an operational efficiency problem that looping helps solve.
I concede that the models are highly effective tools for computational manipulation, sure. But the capacity constraint remains, in my view, the ultimate limiter of what can be manipulated. Let's look at the MMLU categorical analysis again to illustrate this tension. Where are the performance gains most modest, even with maximum looping? While they're on the knowledge-heavy MMLU categories, like moral scenarios that saw only a 7.8% improvement, and global facts, which saw just 8.3%. Now contrast that sharply with the reasoning-heavy elementary math at that huge 155% improvement. This dichotomy is telling, isn't it? When a task requires retrieving specific memorized facts, facts that demand high knowledge density, the benefits of looping diminish drastically. Why? Because the bottleneck seems to revert back to the fixed capacity defined by n, the parameter count. If loop depth were a truly universal scaling axis, we should really expect to see substantial, more uniform improvements across all domains, not just the computationally demanding ones.
That's a fair point about the domain specificity.
And this perceived fragility, it also raises serious questions about stability and scaling predictability. We know from the research that the initial pre-training experiments aiming for deeper recurrence ran into major instability issues. They actually had to dramatically reduce the maximum recurrent steps from 8 down to 4 in the later training phase, stage 1B. This practical difficulty in achieving stable convergence with deeper currents, it's a strong signal that this architecture might be difficult to manage robustly as depth increases.
Right. The stability challenges are definitely noted in the work.
And furthermore, the detailed scaling law analysis itself revealed a concerning trade-off, one tied to the model's optimization process. It turns out that when the model size is insufficient, that is, when n is relatively small, optimizing the total loss via this adaptive mechanism actually results in an observable increase in the shallow stepwise loss.
Okay, let me make sure I understand that.
So you're saying, let me clarify, yeah, it means the model is essentially achieving a lower overall error by exploiting the adaptive loop mechanism late in the process, right? But this comes at the cost of compromising the learning stability and the quality of the early foundational layers. This situation feels a bit like, well, like trying to balance a pencil on its tip. It looks efficient when it works, but it's potentially incredibly fragile to train and suggests the architecture might be trading foundational stability for a marginal overall loss reduction.
Well, while stability is indeed a significant engineering challenge, and they mention needing controls like sandwich normalization to manage gradient dynamics, we shouldn't dismiss the high level of predictability and generality that was ultimately achieved, I think. The LoopLM total loss scaling law proved to be remarkably predictable. It was generalizable with an R2 value of 0.9596 across model size, data size, and maximum recurrent steps. That level of correlation offers a new quantitative framework for predicting performance based on loop depth. which to me sounds precisely like the definition of a viable scaling axis.
A predictable law under specific controlled conditions, perhaps.
And I'm also compelled by some of the qualitative benefits that emerged unexpectedly. Safety alignment, for instance. It actually seemed to improve as recurrent steps increased, even when extrapolating into those untested regimes, t equals 5 to t equals 8. This suggests that the iterative refinement inherent in recurrence might actually aid alignment stability more reliably than it improves pure task performance. If instability were truly fundamental and uncontrolled, you'd expect safety measures to degrade, not improve, upon extrapolation, wouldn't you?
That's an interesting observation on the safety alignment. I'll grant you that.
So let's maybe move our discussion now to the nature of the internal state. I want to talk about faithfulness and the latent reasoning trajectories, because I believe this is a core argument for loop depth as representing a novel kind of capability.
Okay.
Traditional chain of thought, or COT models, they often suffer from what's sometimes called post hoc rationalization, right? They generate a justification after the decision has largely been made internally in the latent space. Loop LM seems to fundamentally mitigate this because the reasoning is latent and, they argue, causally faithful. We see this empirically on datasets like the Quora question pairs. By tracking the step-by-step decision agreement, they found systematic disagreement across steps when t was less than or equal to 4. For example, only about 36.1% of the answers generated at step 2 matched the final answer at step 4. This seems to prove that the model genuinely updates and revises its decision as recurrence deepens. It makes the internal state trajectory a more reliable, traceable reasoning process, unlike the potentially unreliable explicit COT output. This capacity for internal revisable computation feels like a new kind of capability.
Causal faithfulness is certainly a theoretically compelling trade, yes, and I concede that the data showing systematic revision of the latent state is, well, it's a significant philosophical win for interpretability, perhaps. However, the practical architectural gains, I think, are severely undermined by critical implementation dependencies required for actual deployment.
How so?
Well, a naive implementation of, say, a 4-step loop model requires a 4x memory overhead during prefilling. That's because the model needs to store the entire internal state, its key value or KV cache, for every single recurrent step. Now, to solve this significant problem, the researchers had to engineer complex, highly optimized inference solutions, specifically these KV cache sharing strategies, like last-step reuse or averaged reuse. These strategies essentially discard or average the older steps' memories to try and reduce the memory footprint back down towards baseline levels.
Right, the inference optimizations.
Exactly. Without this highly optimized inference path, the supposed parameter efficiency advantage is completely negated by the massive 4x memory cost during that crucial prefill stage. So if the viability of this new architectural scaling access requires such highly engineered, almost post hoc inference workarounds just to achieve a comparable memory footprint, it suggests the innovation is tightly coupled with and ultimately constrained by existing hardware limits. It doesn't feel like a truly independent scaling primitive in the same way parameter count is.
I disagree that requiring clever inference optimization negates the core architectural benefit. I mean, it simply means deployment is resource intensive, which, let's be honest, is true for every frontier model today. The key innovation is the efficiency gain itself. Matching an 8B model with only 2.6B parameters is still the headline. The coherence of the latent states, demonstrated by the faithfulness argument, is robust enough that we can devise these efficient KV cache sharing strategies without suffering a massive performance collapse. That, to me, confirms the stability of the latent representation across steps. The architecture dictates the possibility, the engineering dictates the deployment feasibility.
But that's precisely the tension, isn't it? The efficiency gain relies on leveraging fixed, limited parameters more effectively. If in practice running the model means introducing complex optimization layers that are necessary just to mitigate a massive memory penalty, a penalty fundamentally introduced by the recurrence itself, it really suggests the scaling axis isn't truly independent of the resource constraints defined by the hardware, which relates directly back to the limited capacity N.
Okay, wrapping up then. Ultimately, I maintain that loop LM successfully introduces recurrence as a powerful and, importantly, predictable scaling dimension that's focused on knowledge manipulation. The clear, often dramatic efficiency gains and the demonstrable causal faithfulness of the latent reasoning path establish this architecture as a necessary direction to explore, especially as raw data scaling faces increasing constraints and, frankly, cost barriers. Loop depth offers a pathway to higher capability without necessarily requiring exponentially more parameters or data.
And from my perspective, we certainly acknowledge the immense computational efficiency demonstrated by the Euro family. This offers critical benefits, particularly for deployment in resource-constrained settings, and the work itself is undoubtedly a monumental achievement in model optimization. However, we must remain vigilant that true general capability growth, the ability to store and retrieve general knowledge across all domains, still seems ultimately dictated by the fixed knowledge capacity tied to parameter count. The fragility observed upon extrapolation, the sheer complexity of the adaptive training objective, and the necessity of these highly optimized inference workarounds, they all temper the claim that loop depth is a universally superior scaling axis for foundation models. It suggests instead that it's a highly specialized, parameter-leveraging tool for achieving impressive performance optimization under finite capacity constraints.
So, regardless of where one lands on the axis versus optimization debate, these findings definitely compel researchers to consider not just how much knowledge a model can store,
but how effectively that knowledge can be retrieved and manipulated through internal, perhaps recurrent computation.
Exactly. This shift in focus, whether we ultimately call it a new axis or a profound optimization technique, is undeniably shaping the next generation of architectures.
You know, in the world of AI, for the longest time, the race has just been about getting bigger and bigger. But what if the next giant leap forward isn't about size at all, but about, well, depth of thought? Today, we are diving into a really fascinating new paper. This one's from researchers at ByteDance and some top universities, and it introduces a totally new architecture called Wuro. It's a looped language model, and honestly, it might just change how we think about scaling AI.
So here's the plan. First, we're going to talk about a huge problem in AI right now, what people are calling the scaling wall. Then we'll dive into this really elegant new solution, thinking in a loop. We'll see how it actually performs, and more importantly, try to understand why it works so well. And to wrap it up, we'll look at some pretty unexpected benefits and think about what this could mean for the future of AI. Let's get into it.
All right, let's kick things off. To really get why this new architecture is such a big deal, we've got to first talk about the limits of what we're doing right now.
So for the last few years, the wisdom in the field has been pretty simple, right? If you want a smarter AI, you just make it bigger. More parameters, more data, more compute power. But this whole approach leads to a huge question, one that the entire field is really struggling with right now. Is this path, is it even sustainable?
Because look, this relentless push to just scale up comes at a huge price. We're talking about insane financial costs for training, a bottomless pit of a hunger for more and more data, and you end up with these monster models that are just incredibly difficult to actually deploy and use in the real world. This is the exact problem that people are now calling the scaling wall.
Okay, so if just making things bigger and bigger isn't the answer, then what is? Well, this paper proposes a really cool architectural innovation. It's a shift in focus away from just raw size and towards something more like dynamic, efficient computation. And that brings us to the core concept here, the looped language model, or loop LM for short. So here's the big idea. Instead of building a massive, deep stack of unique layers, a loop LM takes a smaller group of layers and just reuses them. It feeds the output from one pass right back into the beginning for another round. This lets the model get into some really deep computation, basically more thinking, without actually adding more parameters or making the model itself bigger.
Yeah, this diagram really shows you what's going on. Instead of a giant skyscraper with 1,000 different floors, the Wuro architecture is more like a smaller building, but with a super fast elevator. The information can just cycle through that same set of floors, those same layers, over and over again to get more and more refined. It's actually a pretty good analogy for how we think, right? When you hit a really tough problem, you don't magically grow a bigger brain. Nope, you just spend more time thinking it through.
Now, the really clever part here is that exit gate.
See, this isn't a fixed number of loops. The model itself actually gets to decide how much thinking is needed. So for a really simple question, it might just do one loop and say, yep, got it, and exit. But for a super complex reasoning problem, it can choose to keep going, feeding its own output back in for another round and another to refine the answer. This is what's called adaptive computation, and it's the absolute key to making this whole thing both powerful and efficient.
So the theory is really elegant. It sounds great on paper. But the real question is, does it actually work? Let's look at the benchmarks, because this is where these smaller, looping models get put to the test against the traditional giants. And wow, the results are pretty remarkable. Just look at this. The Oro model, with only 1.4 billion parameters, is right there with and sometimes even beating the Qwen 3 model, which has 4 billion parameters. And that's on really tough reasoning tasks. Then you look at the Oro 2.6 billion parameter model, and it's going toe-to-toe with, and in some cases, even outperforming the 8 billion parameter Qwen 3. I mean, this is the definition of punching way above your weight class.
And the difference gets even more stark when you zoom in on one particularly nasty benchmark, MATH 500. Look at this. Azuro, the little 1.4 billion parameter model, just dramatically outperforms models that are more than twice its size. This isn't just a small improvement, you guys. This is a massive leap in capability when it comes to these really hard reasoning problems.
So what this all boils down to is a 2 to 3 times gain in parameter efficiency. Let that sink in. You're getting the performance of a much, much larger model, but in a package that is way smaller, faster, and cheaper to actually run. And that, well, that has massive implications for the real world. Okay, so this is where it gets super interesting, especially from an academic standpoint. Why is this happening? What's the secret sauce? Is this looping thing just some clever trick to cram more knowledge into fewer parameters? Well, the researchers wanted to know too, so they ran some really clever experiments to figure it out. So first thing they did was test the model's raw knowledge capacity. Basically, they asked, how many facts can this thing actually store? And what they found was that both the looped models and the standard ones have pretty much the same storage density, around 2 bits of info per parameter. So right away, that tells us the big performance boost isn't coming from the model just knowing more stuff.
Okay, so if it's not about storing more knowledge, it's got to be about how the model uses that knowledge, right? And bingo, that's exactly what they found. They set up this special task that forced the model to actually manipulate and combine facts it already knew, and the looped models just left the standard ones completely in the dust. This right here is the aha moment of the whole paper.
And this is what reveals the absolute core insight of this research. Looping enhances the model's ability to reason. It's not about how big your library is, it's about how good you are at connecting the ideas from all the different books inside it. We're seeing a fundamental shift here, from focusing on just knowledge capacity to focusing on knowledge manipulation. And it turns out this new way of thinking has some other really profound implications. It goes way beyond just raw performance. It actually starts to touch on two of the biggest, thorniest challenges in AI today: safety and trustworthiness. The paper makes this absolutely critical point. The real thinking, the real causal path to the answer, is happening in the model's internal state, its latent space, as it goes through these loops. This is so different from the typical chain of thought you see from other models, which, let's be honest, can sometimes just be a story the model makes up after it's already decided on the answer. And this visual is just so cool. It gives us a peek under the hood at the model's actual thought process. You're basically looking at a map of how the model's internal beliefs change with every single loop. See how the patterns shift? That shows that its understanding of the problem is genuinely updating and getting refined over time. With a lot of models, you can kind of tell what the answer is going to be pretty early on. But here, you can literally watch the reasoning process unfold. The answer isn't baked in from the beginning, it truly evolves. And here's something they found that was genuinely surprising. It turns out that forcing the model to think longer, just by making it do more loops, consistently makes it safer. The model's harmfulness score just keeps going down the more steps it takes. And get this, this even works when you push it beyond the number of loops it was trained on. It really suggests that this whole process of iterative refinement is, almost by its nature, a path towards safer AI.
All right, so let's pull all of this together. What's the big picture takeaway here? What does this research really mean for the future of AI?
Well, for years, we've basically thought about scaling AI along two main lines. You add more parameters or you add more data. This work proposes a third and maybe even more important axis, loop depth. You could also call it computational depth. The new paradigm isn't just about building a bigger model, it's about giving that model the ability to think for longer.
So to sum it all up, the promise of these looped language models like Euro is a path toward AI systems that are not just way more efficient and capable for their size, but are also potentially more trustworthy in how they reason and safer in how they behave. It's a win-win-win.
And that leaves us with one last kind of provocative thought to chew on. If an AI can get smarter by thinking longer, not just by being bigger, if better reasoning can come from deeper thought rather than just a bigger brain, what does that tell us about the fundamental nature of intelligence itself? Not just for AI, but for us, too. Something to think about.